Hi, welcome to Introduction to Tangent Lines and Instantaneous Rate of Change. In this lesson, we'll be looking at how tangent lines are drawn on a graph, as well as interpreting the slope of those tangent lines, which are leading to a very big concept in calculus, which is the concept of derivatives. Firstly, with tangent lines touch the graph at a single point. Tangent actually means to touch, and more specifically, those tangent lines maintain local linearity with the graph, so it matches the slope of the function. So you should think, is there a slope to reference? And that's how you're referring to local linearity. And a graph will be locally linear if it has a smooth curve at that point. So we need to state a couple of examples of x values that have tangent lines, because there are some x values that do not have tangent lines. So I'm going to draw some coordinate axes here so we can get some examples in. Any continuous function, so we can have a polynomial. So here's just like a cubic. You can draw a tangent line that is going to match the slope of any point on this graph. And we can see that this function has no breaks in it, so it's not discontinuous. And then we can also see that this, not only is this function, this green one I've drawn, is it continuous, but it's also locally linear. So I wanted to draw a polynomial there for you. Some parts of other functions, so like this square root of x, the point maybe at x equals 2, is locally linear, meaning if we were to zoom in really close on the value showing up at 2 for radical x, then, and I can't zoom in too far, but it would look like a line. So it has a slope to reference. A line is the easiest thing to reference when it comes to slope, because it's made up of a point and a slope. And that's what we have with tangent lines as well. We have a point to reference and a slope to reference as well. And then we can also be tangent to a line itself. So the line tangent to this line, for example, is the line itself. And that's because we can reference any point along here, and we can also draw a line that is locally linear to the line that we already have. And examples of x values that do not have tangent lines would include any cusp. So if we were looking at absolute value x, we cannot draw a tangent line at the cusp. We can't just place in a tangent line to the graph because it's not locally linear here. There's no slope to choose from. With a jump or vertical asymptote, there's not a slope to choose from. There's not even a point to choose from with a vertical asymptote. With a jump, there is most of the time there is a point to choose from. We can see that the closed circle is the point we want to reference at this x value. Again, the x value is at these critical example spots. So for a jump in our y values, we can't pick between the two different slopes, whereas these functions might have a slope at either of its ends. We can't pick between them. At endpoints, here we're going to bring up our square root of x idea. The endpoint has no slope. We can't choose any slope there. We can't reference any slope there. And then vertical tangent lines is in our last example where we cannot have a tangent line. So the classic example is y equals the cube root of x where the graph goes through 0, 0, and we can tell that we can draw tangent lines on every part of the graph except for the part of the graph that crosses the origin, because this, if I can draw it more vertically, this slope in the middle of the graph, that slope is undefined. So we cannot have an undefined slope in our tangent line. Right. So basically, our two reasons here is there's not a slope to reference, or there's not a point to reference. Most of the time, it's going to be slope. All right. Now, here's some questions you might run across. Can a tangent line be drawn at x equals -6? Here is -6. We have a point, so yes, we have a point, and yes, we have a slope to reference. For number 2, at x equals -8, we would say no. This is where we have a vertical asymptote. So we have vertical asymptote, but that's not necessarily a reason. We have a vertical asymptote, so there's no point to reference. There's really no point or slope. At x equals -2, we have a cusp. No cusp. So no slope to reference. It's not locally linear. At x equals 1, that's right here. That's looking for that point on the graph. And that would be a yes, we do. We have a locally linear continuous function there, or we do have a point and slope to reference, which is the easiest way to say it. So there you have it. We're just checking to see, do we have a point and slope to reference? So are we experiencing any discontinuities, or do we have any funny shapes like cusps or vertical tangent lines to that would make it not possible to draw a slope at a certain point? Alright, and then we're going to interpret this as a second part of the video. And to do that, I have this graph of turned over quadratic. So the slope of the tangent line is known as the instantaneous rate of change. And we're going to use this idea of the rate of change, and you might have already seen it in physics class, but we're going to use it. And instantaneous rate of change, the rate of change is clearly referencing slope, but the reason why a tangent line is instantaneous, if we can just take maybe drawing a tangent line at this point, is there are an infinite amount of changes, rate of changes. So if we want to know specifically what a rate of change is on the function, then we have to just take the rate of change at a single point. So that's why the tangent line is the instantaneous rate of change. We're going to compare that to the average rate of change here in a second, and I'll show you why the tangent line is much more powerful. So in this graph for x defined on 0 to 8, so we're just looking at this graph from its zeros, so 0 to 8. What are the x intervals with a positive instantaneous rate of change? So I would like you all to recognize instantaneous rate of change as positive slope, and specifically slope for the tangent line. So where can we draw positively sloped tangent lines? And that would be for all of these left hand of the vertex values. So my vertex is at 4, 4. And we can see if we were to draw a tangent line at the very top of this function, that tangent line, that horizontal tangent line that hits the vertex, that uses the vertex as the point it goes through, that has a slope of 0. So all of the slopes on the left side of that vertex have a positive instantaneous rate of change, referred to a positive instantaneous rate of change. So we would say that the slopes we can reference are from 0 to 4 that have a positive instantaneous rate of change. And that's interval notation again. What's the x value where the instantaneous rate of change is 0? So again, what's the x value where the slope is 0? We already answered that question. It's at 4. So we would say just x equals 4. And then what x values have the largest positive or negative instantaneous rate of change for our graph? And so largest positive or negative slope, largest positive slope would be the steepest. So steepest, because that's going to give us the largest slope value. So our steepest, maybe you already know what it is happening at 0. So 0 would be positive, largest positive I should say. And then our other 0 would be our largest negative tangent line slope. and that's at 8. And we can see the spectrum of these tangent lines, and that ought to make sense. As we get closer to 0, a slope of 0, which is at the vertex, then, which is right here, then the slope is going to level out. But as we get further away from it, it's going to be rather flat, and then it'll get steeper and steeper as we go down the sides of this hill, per se. Alright, so the last concept that I'm showing you all is the slope of the secant line, which is the average rate of change. So secant means to cut, and secant lines cross the curve from one point on it to another. So we're going to draw our first secant line at 2, 3, and 8, 0. I'm going to get rid of these tangent lines here. You might want to use a different color if you're taking notes on this, just to reference the two different lines, sets of lines. So there's 2, 3, and 8, 0, and we need to find, and I'm kind of skipping ahead, but we need to find the slope. Oh, so close. I'll take it though. We need to find the slope of this line. So we have to remember some of the old things we reviewed. We'll have to do the change in y over the change in x, which gives us 3 over negative 6. Sweet. So there we have it. We have the slope of the secant line from 2 to 8, and we drew it already. So that's number 9. First part taken care of, and we're estimating the x value where a tangent line has the same slope. So where does the instantaneous rate of change equal the average rate of change? So can you find a tangent line slope that equals the slope of the secant line? Can you guess? I'm going to put my guess down. I think it's somewhere in here, to where these two slopes are parallel. Remember, if slopes are equal, then those lines are parallel. So this means parallel slopes. And it looks like they're equal, and it sure does seem like at a little bit, like between the values of maybe 4.5 and 5.5, we're going to find a slope of the tangent line that is equal to the slope of the secant line. So I'm going to say between x equals 4.5 and x equals 5.5. Alright, so currently we don't have a way to determine the exact slope of any point on the graph. We are just learning how to reference tangent lines, but we will very soon with the next lesson. And that's where I'll end this video. Thank you for watching, and I'll see you all in class. Bye.